Hello, my name is Mark Herring, and I'm an undergraduate peer instructor for digital design this semester. The hope in this course is that in lectures, you get a conceptual and theoretical understanding of digital design with FPGAs, while in lab, you apply those on the practical level. The goal of these videos is to help with your practical understanding of digital design. I'm going to be starting this video by explaining what an FPGA is. In order to explain what an FPGA is, I'm going to be comparing it to a processor, as both are digital devices that are used for computation. Now, a processor you may be familiar with, whether it be from Intro to Computer Organization or microprocessor applications. A processor is each time in the architecture, it's going to have memory, it's going to have an ALU, some form of control to get to the registers, and with that, it's able to do computation defined by the code given to the processor. Now, an FPGA, on the other hand, is going to be given code called RTL, or register transfer level, to be able to create a digital circuit. Now, the advantage to this is that an FPGA can take advantage of something called parallelism, and along with that, it's going to have much faster computation times because of the parallelism, in addition to the fact that it's able to go through a digital circuit designed for this specific application, as opposed to having to go through memory and control and an ALU. A good example of this is your Lab 2 and Lab 3 when creating a Fibonacci calculator. You were given pseudocode that was analogous to C code, and it was about 5, 10, 15 lines of code, white spaces included. It was super easy to make when creating it in the higher level language, but when applying it into an FPGA, you have to create an FSM and then a data path. Now, while it may be a simple application, it's still a good example of how implementing an algorithm on an FPGA is much, much more complicated than implementing it on a processor. But with that, you get the advantages of speed. Because of this, FPGAs are everywhere in the industry whenever speed is of utmost importance. You can see it in the defense industry with the military, or even in things such as high frequency trading. Now we're going to be looking at the VHDL code, which is the RTL of this class. Every VHDL file is going to have two main components with one minor component, the minor component being the inclusion of the libraries. The two main components are going to be an entity that describes the ports or signals or the inputs and outputs of a circuit, and then the architecture, which is going to define the structural or behavioral setup of the digital circuit. Now, I said structural or behavioral specifically because there's going to be two different types of architectures that you can ever create. One will be the behavioral architecture, and the second will be the structural architecture. An example is, think of your favorite Lego Star Wars set. This completed set is a bunch of different tiny, smaller Lego pieces put together. That's an example of a structural architecture. We have many different components connected together to make one bigger circuit, one bigger Lego set. When a behavioral architecture is, back to the Lego set example, is each individual Lego piece. You have to define the behavior of the Lego piece, the color, the number of pieces, one or two sizes long, that kind of thing. So behavioral architecture, you're going to be describing the actual behavior of the smallest circuit. So any digital circuit is going to have a behavioral architecture at the smallest level. So an example for VHDL would be like a 4x1 mux can be created structurally using multiple or three 2x1 muxes. Now that we've broken up the difference between an entity and an architecture, I'm going to be showing the difference between the concurrent execution of VHDL code and the sequential execution of VHDL code. Now here you may notice where I was saying earlier, there's two main components, an entity and an architecture, and I have multiple instantiation of architectures here. You can ignore that because anytime there's more than one instantiation of an architecture, it doesn't matter because only one can be used. So the reasoning for creating multiple is that whenever you instantiate this component that I named test, you can call which architecture you want to use, whether it be concurrent or sequential, and it will use that architecture as the definition of the circuit. Now that we gotten past that, we're going to look at the concurrent and sequential comparatives. So first circuit here, we're going to have concurrent statements, meaning this statement, lines 16, 17, and 18 are all going to execute concurrently, which goes back to what I was talking about, the FPGA, where it can execute things in parallel. And then after that, here, lines 27, 28, and 29 are going to execute sequentially, meaning 27 executes, then 28, then 29. The reasoning that it's able to do that is because it's inside what's called a process. Now, one thing I want to point out about the process is the sensitivity list that's important to know. The sensitivity list is going to include all inputs to the process. Now, this is only going to be for combinational circuits, which I'll talk about in the next video in detail. But to explain the point of a sensitivity list, we'll come down to this architecture, which kind of shows what the inputs of a sensitivity list does. So right here, I have a process, right? But rather than having a sensitivity list, at the end of the process, it will execute and get to line 42 and basically wait on A, B, C, and D, waiting on one of them to change. And whenever they'll change, the process will execute again. So the point of a sensitivity list is just for syntax purposes, basically saying whatever is in the sensitivity list can trigger the execution of this process. One thing I forgot to mention is the circuit that we're creating here, looking at the inputs to the circuit, A, B, C, D, the output of G. If we come back here, we go to the entity, we see we define the same inputs, A, B, C, D, input, standard logic, meaning it's 1 bit, and then G as an output, standard logic, again, 1 bit. And then the purpose of having two architectures here was just to show two different ways of going about of creating the same circuit. I went into Cordis and compiled, and going into RTL Viewer showed this exact circuit here. And after synthesizing and compiling and going into RTL Viewer, you can see that it creates the exact same circuit. And this was the circuit created regardless of the architecture I used. So the point is that you can implement circuits in many different ways, whether it be concurrently or sequentially. Sometimes you can only do with more complicated circuits, one or the other, but another purpose is it's a lot easier to conceptualize something sequentially than it is concurrently, which is the point of having the process. In addition to that, starting to get in a little bit towards the next video, I explained how we have A, B, C, D, and G, looking at the inputs and then the output of the circuit. Then, and right there, you have everything you need to create the entity. But moving on to the architecture, you can see I have E and F here, and I AND to A and B to get E, and then I OR E or C to get F, and then I AND F and D to get G. Coming back to the circuit, that's the exact behavior of the circuit shown in the graphic here. So this is an example of a behavioral architecture because I'm describing what the behavior of the circuit is. So that's what I wanted to cover in this video, just a little introduction and basic overview of what FPGAs are, the two main components of any VHDL file being the entity and the architecture, and then the fundamental difference between any concurrent executions inside of an architecture and then any sequential executions inside of an architecture. I also described the differences between behavioral and structural architectures, which are going to come up in every single video, and I go into more details later on.